So by now, hopefully you've given some thought to this problem here, right? We had, in the last video, talked about how we can find a way to color each of these regions here so that any two regions that share a border have a different color, right? We want A and B to have a different color because A and B share a border. We want A and L to have a different color, A and M to have a different color, etc. So you can go through this yourself and see how many colors it requires, and you could try to go through it with guess and check, but we're going to see how we can try and turn this into a graph theoretical problem instead. All right, so this is what we're going to do. We're going to take each one of these, I've already labeled them. Take each one of these regions and give them a label, some sort of a name here, so that we can tell the difference between them. And then we turn it into a graph by letting each region become a vertex. Okay, so our vertices would be A, B, C, D, etc. And each border becomes an edge. Right, there's a border between A and B, which means there has to be an edge between A and B. Okay, so we can turn this into our graph like this. Maybe you can't see the whole thing, but we can see that, for example, A has a border between, there is a border between A and M, A and L, A and B, and A and C. Right, there's borders between all those regions, so we would have to draw an edge between vertices A to M, A to L, A to B, A to C. Okay, and you continue in that way, so go on to B. B is connected to A, we already drew that, but B is also connected to C, D, K, and L. So I'm going to go back here and draw an edge to C, to D, to K, to L. All right, so that takes care of vertex B. Then we go back to region C. It's bordering region A, region B, region D, and region E. I already have A, B, so then I would put in D and E, and we continue in this manner. I don't want to spend too much time on the video in this part, and so I've completed the graph over here. In the end, your graph should look something like this. Okay, so what is the purpose of doing this, right? How does this really help us to answer the question? Well, what we're really doing in this problem is we're trying to figure out how can we color the regions so that any regions that are bordering each other have a different color. In the graph theoretical version of this, we're trying to color the vertices, right? Because regions represent vertices. So we're trying to color the vertices in such a way that any two bordering vertices, any two vertices that are adjacent that share an edge, have a different color. So what we're looking for here is something that we call a vertex coloring, and in particular, we want a proper vertex coloring. So we say that an assignment of colors to the vertices of a graph is called a vertex coloring, and such a coloring is called proper if every pair of adjacent vertices has different colors, right? If two vertices are connected to each other, like M and I, we want them to have a different color. Because remember, those vertices M and I are representing regions that border each other, so we want two bordering regions to have a different color. Right, so what we're looking for is a vertex coloring. And we want to make sure that we're using as few colors as possible. That's what the problem asks us to do. It's asking us how many colors do we really need here. And so let's just go through and see what we can do here if we try to color these vertices. Now, it's still sort of a matter of guess and check, but what we need to consider is the fact that some of these vertices have a lot of other vertices adjacent to them, right? Have a lot of neighbors. For example, L is connected to a whole bunch of different states here, to A to B, to K to J to I and M. Vertex K here has a lot of connections as well. And so let's just sort of start going through and try to give colors to these vertices. I'm going to start in the middle with K. So I'm going to color this purple. And it might be hard to see, so I'm also going to label it 1, say purple is our color 1. Now, I know that B, D, G, J, and L all have to have a different color than purple, right, than that color 1, because they're all adjacent to K, and K we've already colored as 1. Now, does that mean we need 1, 2, 3, 4, 5 more colors? No, right, because if we color B something else, like blue, B for blue, and I'll label that second color 2, I don't have to give L and D two different colors from each other, as long as L and D are each not 1, right? Not purple and not blue, not 1 and not 2. right? D and L aren't adjacent to each other, so they're allowed to have the same color as each other. So let's call them both pink vertices. Let's call them color 3. So our pink vertices, we're going to give a 3. Okay? And just like before, we've still got to color J and G. Now J can't be colored 3 and it can't be colored 1, but it could be colored 2, for instance, because so far our only blue vertex, or only 2 vertex, is vertex B, which is not adjacent to J. So let's reuse our color 2 here. Okay. But now what's going to happen with G? Because vertex G is adjacent to J, to K, and to D. It's adjacent to a blue, a purple, and a pink vertex already. Which means I can't color it blue, I can't color it purple, and I can't color it pink. All right, now we do need for sure a fourth color here. Let's color this one red. And call red color 4. Okay. So we're going to need at least 4 different colors to color this map, but from here let's just go through and see if we can choose different colors each time. Maybe I'll go to I. I can be anything except for pink, blue, or red, so maybe I'll color I purple. That's my color 1. Then H can be anything as long as it's not red or purple, so maybe I'll color it blue. Blue was color 2. F can't be red and it can't be blue, so I'll color that one purple again. That was my color 1. All right, E, it can't be pink, can't be red, can't be purple, so I'll color that one blue. All right, you have various options at each case, but as long as you're coloring it in such a way that it's not the same color that you already used for any of the neighbors, then that's a proper coloring. All right, vertex C is connected to a blue, a pink, and a blue, so it just can't be any of those. Maybe we'll color it red. All right, red was color 4. A can't be pink, blue, or red, so let's color A purple. Let's color 1. M can't be purple or pink, so we'll color that red. Just color 4. And we're done. All right, we were able to do it using 4 different colors here. All right, so we say that since this graph required 4 different colors, and we know that it required 4 because of this issue with K in the middle, right? K was connected to these 5 vertices around the outside. There's a little cycle around them. And we couldn't color it with less than 4 because going around that 5 cycle here is going to require 3 different colors. So we would say that this graph requires 4 different colors in order to be properly colored. We call that the chromatic number of the graph. So the chromatic number of the graph is the smallest number of colors. The smallest number of colors required for a proper coloring. And the notation we use for that is it looks sort of like a capital X, but it's a Greek chi of G. So the chromatic number of this graph, because it required 4 colors, we would say the chromatic number of this graph is 4. And looking back at our original map, that means that our map requires 4 different colors. And so we can figure out what the colors are using the proper coloring of the graph, right? So we colored A, K, I, and F purple. So looking back at our graph, let's see where I labeled it. A, K, oh, nope. Oh, crap. Oh, God, no. Oh, no. It's okay, it's okay. I thought for a second that K and I were adjacent to each other. Right, they're not. Right, K and I can have different colors because they're not actually touching. Oof, that was a close call. K and I are allowed to have the same color. Oof. Okay, and then what was our last purple vertex? F. So F as well is going to be purple. All right, then we had our red region, so one labeled 4, that was C, M, and G. So we color C, M, and G with our red. Our pink vertices labeled 3 would be D, and L only, so we would color D and L with pink. And finally, our blue vertices were B, J, H, and E, which were the last four. Okay, so we could color these last guys blue. And this is going to give you a coloring of the map so that any two adjacent regions have different colors. All right, so we use the graph, right? We use this idea of a chromatic number of a graph, or a proper coloring of a graph, to solve our original problem here, right? And we can see that there's actually lots of different scenarios where finding a proper graph coloring will actually solve a problem for you. But before we go to those, let's do a couple of practice problems here. We're going to try to find the chromatic number of each of these three graphs. Remember, the chromatic number is the number of colors you would need, the smallest number of colors you would need to properly color the graph. So we have three different graphs here, and we can try to go through and guess and check these. For example, if we were to properly color this first graph here, let's start somewhere, right? All of these, this is sort of a symmetric graph, right? Every vertex is attached to every other vertex with an edge, which means it doesn't really matter where you start. I'm going to color this first vertex purple, label it 1. Well, that means that this vertex that's adjacent to it can't be colored purple because it's adjacent, so it needs its own color. Let's say 2. Then we move to our next vertex down here. This is adjacent to both the vertex labeled 2 and the vertex labeled 1, which means I can't use that purple or that red for this vertex, so I need a new color, say blue or 3. And it's going to keep going like this. Because every possible edge is already in this graph, I'm never going to be able to reuse a color because every vertex is adjacent to every other vertex. So I need a new 4th color green here. I need a new 5th, I'm running out of colors, but I need some other color, let's say black, down here. And then I need a 6th color for my last vertex. Maybe I'll just reuse a different purple here. Right, that's a different color. Right, so actually here, because we required 6 different colors, our chromatic number is 6. All right, now in the second graph, we can go through and do the same thing. Again, we have some symmetries here, so start somewhere. Let's say I labeled this first vertex color 1. Then none of these vertices can be colored 1, but they might be able to be colored something, right? We might be able to reuse one of our colors, say for these 2 vertices at the bottom, because these 2 are not connected to each other, so they're allowed to have the same color. Let's say I colored both of these 2. Okay, well, now I need to color these 2 vertices as well. They can't be colored 2, they can't be colored 1. So what do I do here? Do I need 2 different colors here? Actually, you could try to do it that way. Let's say color this 3 and color this 4, and then choose some last 5th color for the, or actually, reuse either 1 or 2 at the top. So color that 1, for instance. So this is a proper coloring of the graph. However, it's not really optimal. We can actually do better than that. So if we redraw this graph down here, we have our 6 vertices. We can start with the triangle in the middle and say, I know that this is a triangle, so we need 3 different colors around the middle. Let's call them colors 1, 2, and 3. Having colored these 3 with 3 different colors, we can actually now make sure that the remaining 3 vertices on the outside are properly colored using those same 3 colors we already have, right? So this one on the outside is connected to a 1 and a 3, which means we can color it 2. And this one on the corner down here is connected to a 2 and a 1, so we can color it 3. And the vertex on top, of course, is adjacent to a 2 and a 3, so we can color it 1. And now we've actually found that we can color it using 3 colors instead of 4. Right, so our proper coloring up here, even though it's proper, it's not an optimal coloring because we can do it in fewer colors. So that's why it can be kind of hard using just a guess and check method to figure out exactly what the chromatic number is here. So is the chromatic number really 3, or could we do it in any fewer than 3? I think it's clear to see that we need 3 colors because we have this triangle, for instance, in the middle. There's no way to color these 3 vertices using any less than 3 colors because they're all connected to each other, right? They all need their own separate color. So we can say in the second case that the chromatic number of this graph is 3. And finally, in our last graph here, again, you can try to use guess and check, but we'll see that if we color the vertices in the top row the same color, let's give them both the color 1, for instance. They're not connected to each other, so they can have the same color. And we color the vertices in the bottom row some other color, let's say red or 2. It's possible to color this graph properly using only 2 colors. We're going to need certainly at least 2. It couldn't be any less than 2 because there's edges, so we need at least 1. So the chromatic number of this third graph is 2. Okay, now notice that one of the hard parts of figuring this out is if you sort of make a mistake in your guess and check, it can sort of lead you to think that there's a higher chromatic number than there actually is. And so one thing to look out for when you're doing this is you want to try to find things like triangles or things where you have a subset of vertices that are all connected to each other, that have every possible edge between them. In this graph here, we have 3 vertices that are all connected to each other, and that told us that our chromatic number was at least 3. It's giving us a lower bound on our chromatic number. In this first graph here, actually every single vertex is connected to every other vertex. So this has a property that there's 6 vertices with every possible connection between them. Right, we call this graph, this subgraph that has all possible connections between it, a clique or a K-clique. So in a graph G, oops, let me zoom out a little. We say that a K-clique is a set of K vertices in the graph that has every possible edge between them. And the clique number of the graph is the largest K-clique that you can find. So in this example here, we have 6 vertices all together, and let's see if we can figure out some cliques here. Now, a 3 clique is just a triangle, right? It's 3 vertices with every possible edge between them. Our last graph in the middle had a bunch of 3 cliques. This graph certainly has a 3 clique. For instance, if you look at vertices 4, 3, and 2, it's a triangle. It's every possible edge between them, so there's a 3 clique. But you can actually do better than that. There's actually a 4 clique here. I'm going to try to highlight it. If you look at vertices 1, 2, 3, and 4, it has every possible edge between them. And so it has what we call a 4 clique. Now this doesn't actually have a 5 clique, right? There's no 5th vertex you can add that has every possible edge between them, right? 5 doesn't make this into a 5 clique because 5 is not connected to 2 or 3. Similarly, 6 isn't connected to 2 or 3. And no other selection of 5 vertices is going to have every possible edge between them as well, which means the largest clique for this graph is this 4 clique that I highlighted, which means the clique number of this graph is 4. Now what does that tell us in terms of a graph coloring? Well, if we have a 4 clique, then we know that each one of these 4 vertices is going to need its own separate color, right? So we know that the chromatic number is at least 4. And in fact, in this case, it's going to be exactly 4 because you can just choose 4 different colors, let's say 1, 2, 3, and 4, and then color your last 2 vertices using the 2 colors that these 2 vertices are not attached to. For example, color them 2 and 3. Okay, and so this has a chromatic number of 4, but in particular what we know is that because there is this 4 clique, because there's 4 vertices with every possible connection between them, the chromatic number is at least 4. That's what the lower bound theorem tells us. It says in a graph G, if G has a clique number of K, then the chromatic number chi of g, right, the number of colors you need for proper coloring, the smallest number, is at least k. It's greater than or equal to k. So if you have such a k-clique, k vertices that are all connected, you're going to need at least k colors, possibly more. And to give you an example of when you might need actually more than the clique number, just look at that graph that we did together, that big one. This has a clique number, in fact, of 3. Right, the largest subgraph you can find with every possible connection between them is a 3 clique, it's a triangle. And so the clique number of this graph is 3, but we found that it actually required 4 different colors. So the lower bound theorem doesn't tell you necessarily the chromatic number of the graph, it's just giving you a lower bound. It's saying you need at least this many. Okay, so graph coloring is actually a pretty hard question. It's one that mathematicians have been studying for a long time, and they don't really have like a nice computable, great, or a very quick way of finding the chromatic number of a graph. Right, so it's a hard problem, but it's a way that's going to solve a lot of different problems. And we'll see in the exercises just exactly how you can turn different problems into a graph and look for the chromatic number to help solve that problem.